to the work of Beltrami and Jordan in the 1800s, where the question is simply that one is given a data set, which in this case is illustrated by the set of blue points, and the goal is to fit a low-dimensional subspace to this data set. So here I assume that the ambient dimension is capital D, and the dimension of the subspace is little d. And I have endpoints. And we know that when the data points are noiseless, and there is no outliers, this problem can be solved simply by computing the singular value decomposition of the data. And the left singular vectors give a basis for the subspace, and the number of non-zero singular values gives the dimension of the subspace. In practice, however, data sets are not as clean, and so it's often the case that data are corrupted by both noise and outliers. Outliers here are assumed to be just points that are far from the subspace and illustrated here by the red points. And so in this particular case, I'm going to denote by M the number of outliers and N the number of inliers. And the inliers are the points that perfectly lie in the subspace. And so what I observe now is this matrix X tilde here on the left. And I don't know a priori which points are in the subspace and which points are outside the subspace. And so the matrix X tilde is not perfectly ordered as inliers first and outliers first. It's up to an unknown permutation. And the key challenge is that the singular value decomposition of this now corrupted data matrix may be very far from the singular value of the X matrix, which is the one in the subspace. And so even one outlier might make the classical PCA method based on SVD give a completely wrong solution. So this has motivated many methods for trying to deal with the question of robustly estimating the subspace. And there are many of them. So let me just mention four here in the next 4 slides. So one of them, the name of it is random sampling and consensus, and the name is RANSAC, is based on the idea that if the dimension of the subspace is small, imagine here, for example, this was just a plane in R3, then I can just sample, let's say 3 points. The 3 points define a plane. And if I get lucky, these 3 points are all inliers, and then I can just count how many points are well fit by that subspace. And if there are many of them, then I can assume that that's a good plane. Now, in practice, of course, when you randomly sample 3 points, it's not going to be the case that they're all inliers. So you just keep sampling many times. But the idea is that eventually you will find a good plane that has sufficient support, support in the sense of consensus, sufficiently many points within the outlier. And so this method has been studied for a while and is known to work well when the dimension of the subspace is small and the percentage of outliers is not too much. As you can imagine, right? If the vast majority of the points are outliers, then the probability that when you sample D of them, they come from the subspace is going to be very small. So that's why this method requires the percentage of outliers to be small and the number of outliers, the dimension of the subspace to be small. So another method, this is more recent, 2010, that is very popular. It's based on sparse plus low rank style decomposition. So these all emerge as extensions of compressed sensing type approaches to matrices. A famous method was the method from Emmanuel Candes, or based on nuclear norm minimization. So this is an extension where what you say is, okay, I'm just going to decompose my data matrix as the sum of a matrix of inliers plus a matrix of outliers. And therefore, I'm going to enforce that the L matrix needs to be low rank, because it's only going to contain the inliers, and the E matrix needs to be column sparse in the sense that only a small percentage of the columns will correspond to the outliers. And then you just seek a convex surrogate, which is the nuclear norm plus the 2,1 norm of the matrices L and E respectively. And again, this method works very well. In fact, you can prove that you perfectly recover the subspace and perfectly recover the outliers, provided again that the dimension of the subspace is small relative to the ambient dimension, and also provided that the percentage of outliers is small. In addition, there are other technical conditions like incoherence that is required. So that's the second method. A third method developed by Emmanuel Candes is based on the intuition that inliers are linear combinations of each other, while outliers might require many data points if you try to express them as linear combination of other points in the data set. So this idea that if you take a point and you express it as linear combination of other points, and then you search for sparse representations, then the inliers will have a sparse representation, but the outliers will not. And again, this method can be proven to recover the inliers appropriately, but again, it requires the dimension of the subspace to be small relative to the ambient dimension, and the distribution of both inliers to be well distributed. Typically, what you do is that you assume that the data is normalized, so everything is in the unit sphere, and so outliers well distributed means well distributed in the ambient sphere, for example. And last but not least, there is a method from Lerman that is based on finding a orthoprojector P from the ambient dimension to the subspace. And instead of enforcing the rank constraint so that you get a low dimensional subspace, that would be a non-convex constraint, you typically relax it and you require this orthoprojector to belong to the positive semi-definite cone, and you enforce a constraint on the trace to approximate the rank D constraint. So this method is called Reaper, and you will see in a moment that it's currently one of the best methods. So in fact, let me show you how these methods actually work in practice. The x-axis here denotes the outlier ratio, so the percentage of outliers relative to the entire data set from 10% to 90%. The y-axis denotes what we call relative dimension, so the dimension of the subspace relative to the ambient dimension. Here the ambient dimension is 30. And white denotes success, namely that you were able to perfectly recover the subspace. This is in the noiseless case. And black means that you did not perfectly recover the subspace. And here many trials are done. And so we are reporting here the percentage of the time that you correctly recover the subspace. And as you can see, it works very well, as I already stated, provided that the dimension is sufficiently small or the percentage of outliers is sufficiently small, but clearly fails in the high outlier ratio and high relative dimension domain. So this is the case for Ransack, but this is also the case for the sparse plus low rank decomposition method. It's a little bit better. This is the self-expressive method from Candes, and this is the Reaper method. And clearly, I hope you appreciate that the Reaper method is clearly better in the sense that the percentage of the time that it works is higher. But all these methods fail when the dimension of the subspace is high relative to the ambient dimension. For example, hyperplanes in this case would have dimension 29 relative to the ambient dimension 30. Now, why do we care about those cases? I mean, much of the theory typically assumes that subspaces are low dimensional. Well, there are many applications where this is not the case. So planes in R3 is one of them, and there is point cloud data that it's very commonly used in many applications today, particularly for robot navigation when you need to detect planes as the robot navigates an environment. A second example that is common in the computer vision literature, where you're trying to match two pictures, and you do that by figuring out what point in one image corresponds to which point in another image. You need to estimate the relative rotation and translation between the two images. So that problem can be translated into estimating what is known as a homography, for example. And in that case, you need to estimate planes. or hyperplanes. And typically, for example, the ambient dimension might be 27, and you need to estimate hyperplanes in that space. And so this is a second example where subspace estimation is needed. And here the robustness issues come because this matching of one point from one image to the next is very, it could be incorrect. Like in the case of windows, every window matches every other window. So you could have a lot of wrong matches. And so the percentage of outliers could also be very large in practice. In fact, it could be well 80% of your matches are wrong. And so dealing with these situations where the dimension is high relative to the ambient dimension and the percentage of outliers is high is important for these applications. There are many others that I won't discuss today, but in dynamical systems, identifying the parameters of a linear dynamical systems is another example. And in deep networks, we have observed experimentally that if, say, you pass the ImageNet data set through a network like AlexNet, then the features that are extracted at the output of the network, which are typically of dimension 4,000, their dimension for a single class might be also nearly 4,000. So these are examples where the features extracted by deep networks are also describing high dimensional subspaces as opposed to low dimensional subspaces. So what I'll be presenting today is this method called dual principal component pursuit, or DPCP. And here's the performance on the same data set that I was talking about earlier. And I hope you appreciate that is the only method that is able to get a good performance for this high relative dimension case. And in fact, you can see that it can perfectly solve the case where the dimension is 29 out of 30 in this particular example, even with up to 60% outliers. And it only begins to fail around 70%. Okay? And by the way, all other methods, as you could see, they could even tolerate 90% outliers, but they required the dimension to be about a third of the ambient dimension. So how does DPCP achieve this? What is quite remarkable is that it's solving a very simple optimization problem. So here B denotes the normal to the hyperplane, and X tilde is the data. So this is really, at the end of the day, an L1 minimization problem on the sphere, subject to a spherical constraint because the normal to the plane is chosen in this particular case to be unit norm. Why this is a good objective and where does it come from? That's part of what the talk is about, and to convince you that this is a good optimization problem to solve here. But the challenge, as you can see, is that it's both non-smooth as well as non-convex because of the spherical constraint, and therefore is not necessarily straightforward to solve. So this is what I'll be talking about today. So the first part is going to be analyzing this optimization problem. In particular, what we would like, right, is for the global minimum to this optimization problem to give you a true normal to the subspace. So the first question we will ask is, what are the conditions under which the global A, or any global minimum, perhaps it might not be unique, any global minimum to this problem is orthogonal to the true subspace. And I'll present a geometric analysis that essentially says that if the inliers and outliers are sufficiently well distributed, then any global minimum to this problem is orthogonal to the true subspace. But that's just going to be a geometric analysis, effectively characterizing the landscape of this optimization problem, not yet any algorithm that would actually find the global minimum. So that's going to be the second part. I'll also present, though, a probabilistic analysis that effectively just depends on dimensions and percentage of outliers. And I'll be able to show that this optimization problem has the property that if the number of outliers is actually quite large meaning in the order of the square of the number of inliers, then any global minimum is orthogonal to the subspace with very high probability. High probability typically here means something like 1 minus something small, and that something small is going to be on the order of 1 over n, where n is the number of data points. The second part of the talk will focus on algorithms, whether we can design algorithms for solving these non-convex and non-smooth problem that have guarantees of converging to the global minimum. And I'll consider maybe the simplest possible algorithm you could imagine, which is just a subgradient method. And we will show that it probably converges to a global minimum of the optimization problem with a piecewise linear rate. And again, the sufficient conditions under which this is the case require the inliers and outliers to be sufficiently well distributed, plus a mild condition on the initialization that needs to be sufficiently far from the true subspace. So somewhat similar to the requirements of, say, the power method for computing eigenvectors of a symmetric matrix. And last, I will present some examples on some of these geometric computer vision problems and demonstrating the effectiveness of the approach in practice. Before I begin with the technical part, maybe if there is any question, I'm happy to entertain it now. No. Okay, so let me begin with the geometric analysis. So again, let me repeat the notation that I introduced earlier. So we've got data X, we have n points, and those are the ones that lie perfectly in a subspace. And then we have outliers, and we have capital M of them that lie outside the subspace. And X tilde is going to denote both the inliers and the outliers. And again, as I said earlier, we assume we don't know which points are inliers and which points are outliers. So that's why the X tilde matrix is up to some unknown permutation here. Capital L is going to denote the total number of points, both inliers and outliers. So the dot product between any point, X tilde, and a normal vector B to some hyperplane effectively is the sign distance from that data point to the hyperplane. And this is going to become important because what we really are going to be trying to do is the following. This dot product is 0 if the point belongs to the hyperplane and non-zero otherwise. Therefore, the number of non-zero entries of this vector is the number of outliers. So what we're going to do is to try to find a vector B here that contains such that the hyperplane contains as many points as possible. So in other words, what we're doing here is minimizing the number of outliers to that plane B. And a priori, the B can be any vector. It doesn't need to be unit norm. So I'm writing here that it just needs to be non-zero because otherwise the global minimum to this problem would be B is equal to 0. Now, so written in a little bit more detail, this is exactly what I meant. The number of times that the dot product is larger than 0 in absolute value, that's going to be the number of times that the number of points that are not contained in the hyperplane. And so that's what we want to minimize, the number of outliers to the hyperplane. And we are going to, this is arbitrary, so we could have done any norm here, but for the sake of convenience, we're going to choose the 2 norm so that the normal to the hyperplane is unit norm. And then the next part we do is that we relax this counting norm to an L1 norm of this vector. And therefore, the objective is nothing but the sum of the distances from the data points to the hyperplane. And so again, those distances should be 0 if the hyperplane is the true hyperplane for the inliers and non-zero only for the outliers. So at the if it was the case that the global minimum is given by the true normal to the hyperplane, then the minimum objective is really the sum of the distances from the outliers to that hyperplane. All right, so that's the problem formulation. So again, the question we're asking is why this relaxed objective has the property that the global minimum is really given by the true normal to the hyperplane. And so the geometric analysis will rely on some quantities that characterize the geometry of the problem. So the first thing to note is that the objective can always be written as the objective on the inliers plus the objective on the outliers. And what we're going to do is to define a few quantities. The first one was already in the paper by Lerman et al. And as you can see here, what it measures is, well, I think we have to be a little bit careful. The B now is not an arbitrary vector. It's going to be a vector in the unit sphere and also in the subspace. And maybe I should point out a few assumptions we're making here on the data before I get started. So the assumptions are that we are going to assume that all data points are a unit norm. So the geometric picture to imagine here is that I've got a sphere, as I'm illustrating here. Now, in this sphere, the data points in the subspace, because I'm assuming that they're all unit norm, if the subspace is, say, the equator, then the data points are actually going to be in the intersection of the subspace with the ambient unit sphere. On the other hand, the outliers are going to be arbitrary points that are on the ambient unit sphere. So all columns of O and columns of X are a unit norm. Okay, so that's a picture to have in mind. And so what I'm talking about here is that if this here is my subspace S, so what I've done is to choose a vector B in that subspace in this particular case, and consider the dot product with all of the inliers. Okay, and that's what the quantity CX mean denotes here. Now, what are the properties of CX mean? So if the data were to be all oddly distributed along one line, once you project it, it's going to be all concentrated in some particular region, then you can get this number to be 0 because you can choose B to be perfectly aligned with the data on the equator. On the other end, if the data is well distributed in the subspace, once you project it, then it'll be well distributed on that circle that I draw on the top right, the circle of blue points. And therefore, this quantity is going to be larger. So the main point is that the better distributed the inliers are, the larger this value of CX mean. So CX mean therefore characterizes the distribution of the data, and it measures how well distributed it is. The second quantity that I want to mention here is the following. This is now going to be the subgradient of the objective for the outlier term. And this subgradient of the objective is denoted here, O times the sine of O transpose B. And this subgradient is going to be projected orthogonal to B. And so what can happen here is the following. In various ways, if you think about it, the O, the columns of O is the matrix of outliers. So the sign pattern by which it is multiplied on the right is just going to be +1 or -1 or zeros. And therefore, it's sort of a weighted combination of the columns of O. So in a sense, it's sort of a weighted average of all of the outliers. So if it so happens that all of the outliers are concentrated in some particular region, then if you give me any vector B as illustrated here on the left, right, the weighted average is going to be this OB vector. And I can always choose this B so that it is orthogonal to OB and therefore make this eta O 0. Okay. Conversely, though, if the outliers are well distributed in the ambient space, then I cannot choose any B that will make it orthogonal to the OB. The OB will, yes, because the OB would always be somewhat aligned with B. Why? Because of the sign pattern, right? So it is a weighted average, but you always put the signs. Therefore, all of the weighted average will be aligned with the vector B. So in other words, if the outliers are well distributed, then I can get the eta O to be 0, while if the outliers are badly distributed, concentrated in a particular region, then I can get a large value for this quantity. And the last ingredient of the theory is this kappa quantity that, as defined on the top, measures the largest sum of distances with respect to some hypothetical hyperplane B minus the smallest distance. And I'm not going to get into the details again, but I think it's easy to convince yourself that if the data is very well concentrated, then these two numbers are going to be very different, because I can always choose B that is well aligned with outliers and then maximize. And so the first number is going to be large, and I'm going to choose a different B that makes the second number small. And so that the gap between the two is going to be large. But if the data is well distributed, the sum of the distances, the maximum or the minimum, is going to be about the same. So the better the outliers are distributed, the smaller this kappa quantity. So to summarize, just flash briefly, we have this C quantity that measures how well distributed the inliers are, and we want it to be large for well distributed. And we have this eta O needs to be small if the outliers are well distributed. And similarly, the kappa needs to be small if the outliers are well distributed. So with those quantities in mind, we can begin now the analysis of the landscape and of the geometry of the optimization problem. So the first theoretical result says that if I look at the optimization problem, what are the critical points? So the critical points are either going to be orthogonal to the subspace. So thinking about the picture here on the left, the yellow is the subspace. The orthogonal complement is S perp, and then I'm considering a normal vector B that makes an angle theta with S perp. And ideally, I would like the global optimum to be such that theta is 0. That's what I'm trying to understand. And so the question is, what are the critical points, and whether 0 is a critical point, and what are the other critical points beyond 0? So what this lemma says is that the critical points are either in S perp, meaning that theta is 0, or have an angle theta that is large. Large, and how large? It depends on M, which is the number of outliers, N, which is the number of inliers, and these quantities that I talked about earlier. Cx min, that characterizes how well distributed the inliers are, and eta O, that characterizes how well distributed the outliers are. And so what this is saying, interestingly enough, is that in this half sphere, there is no critical point in the middle. So either is the North Pole, which is the true normal to the hyperplane that we want, or it is far from the North Pole and near the subspace. And that's what the critical points are. Why far? Well, of course, it will depend on what M, N, and eta are, but you can clearly immediately see, right? If M, the number of outliers, was small, then this angle is going to be closer to pi over 2. So this means that there is no critical point in the middle, essentially. More specifically, and we're going to see that in a moment, it can be proven that the Cx min, so let's assume, for example, that the ratio between the number of outliers and the number of inliers is fixed, M over N is fixed, and that I'm letting N go to infinity. So it can be proven that Cx min goes up and converges to a fixed constant that depends only on little d, which is the dimension of the subspace. It can be shown that eta O will go to 0, and that theta sharp which is the lower bound on the angle for the critical points, will go to pi over 2. So in other words, what this says is that as I increase the number of data points, the angle theta sharp is just getting bigger and bigger, and therefore there is essentially no critical point in between. It's either the North Pole, which is the global minimum, or it's going to be almost on the subspace regarding the critical points. The next result characterizes not just the critical points, but the global minimum. And it requires a little bit more, and the theorem is at the top. So M again is the number of outliers, and N is the number of outliers. So immediately you can get there is a factor that is the ratio of the two. So I want that ratio to be smaller than something. So so intuitively that makes sense, because I want the number of outliers not to be that large. The CX mean shows up at the bottom, and remember that it's larger when the data is better distributed. So the better distributed the data, the easier to satisfy the theorem. And then in the numerator, we have the distribution of the outliers, the eta O part and the kappa O part. And both of them get smaller and smaller as the number of data points goes to infinity. And eventually, actually, they get to 0. So that's why the probabilistic analysis is going to hold true, because as n goes to infinity, we're going to get that we're going to ask what is the probability that the left quantity is less than 1, and that probability is going to go to 1 in the probabilistic analysis. Okay, so with that in mind, then, before I just move to the probabilistic analysis directly, the main point is that we have a theorem that says that any global solution to this L1 minimization problem on the sphere gives you a vector that is orthogonal to the true subspace. And that in order for that to be the case, you simply need that the outliers are well distributed in the ambient sphere, and the inliers are well distributed in the subspace. Okay. And that's what this theorem is trying to characterize. So let me now move into the probabilistic analysis. So the probabilistic analysis really starts directly from the geometric condition, and now under some generative model for both the inliers and the outliers, it tries to assess what is the probability that the quantity on the left is smaller than 1. And so this is the probabilistic model. So we assume that the inliers are drawn uniformly at random from the ambient sphere. So maybe I'm going to redraw what I had done earlier, where this is the ambient sphere. And so what we're assuming is that the inliers are drawn uniformly at random, say from the equator here. Okay. And then the outliers are going to be drawn uniformly at random from the unit sphere. Okay. So with that in mind, the CX mean quantity that goes into the denominator, you can prove that with high probability is larger than a quantity that's on the order of 1 over the square root of the dimension of the subspace. Okay, and again, we want the outliers to be well distributed, and that means that the CX mean needs to be sufficiently large. Then for the outliers, it can be shown that with high probability, the eta O quantity is bounded above by a constant times something that is 1 over the square root of the outliers, 1 over the square root of m. So that's true of both kappa O and of eta O. And now, with all of these concentration inequalities, we can substitute them into the original geometric condition to get the main result. And so the main result is that any global solution to the DPCP problem must be orthogonal to the true subspace with probability 1 minus O of 1 over n squared. N is again the number of inliers. If the number of outliers is bounded above is on the order of n squared. So let's forget for the time being about the constant. I'll return to it. But this is, I think, a very important result from the perspective that the number of outliers, m, that can be tolerated is quite large, on the order of the square of the number of inliers. And this is illustrated here with this picture that, again, the x-axis is the number of inliers, the y-axis is the number of outliers. White denotes success, namely that if you run, if you find the global minimum of the DPCP problem, it is equal to the true normal to the subspace. And 0 means that you did not succeed. And so this, there is, as you can see, something like a phase transition occurring there between the white region and the black region. And the boundary of where that phase transition occurs can be well approximated by O of n squared. This is what this picture is illustrating. Okay, so let me now compare this with other results. So if we look at alternative methods in the literature and how many outliers they can tolerate, you can see that all existing results, the number of outliers that can be tolerated is typically linear in the number of inliers. So the big improvement here is that it's quadratic. Now, that comes with a little bit of a cost, which is what is the constant in front of it, and how does that constant depend on the other quantities for the problem, which are the ambient dimension as well as the dimension of the subspace. So with respect to, say, the geodesic gradient method, we are doing much better, right? Because that method has square root of the ambient dimension on top. Sorry, I should say the other way around, much worse, right? Because if the capital D is large, this means that you can tolerate less outliers. So with respect to many of the methods, I think the issue is that we have here is the capital D dimension. Okay. Okay, so that was the analysis, both geometric as well as probabilistic, of these DPCP algorithms. So sorry, of the theory and essentially what I've said so far is that if the outliers and inliers are well distributed, the global minimum to the problem is the true normal to the subspace. So the next part is really, well, can I construct algorithms that are guaranteed to converge to that global minimum? So we've developed a variety of algorithms, and the theory is not complete. For some of them we have theory, and for some others we don't, and I'll mention what we have. So the first algorithm is based on solving a sequence of linear programs. The idea is essentially the following. We have to minimize that L1 objective subject to a unit norm constraint. So what we do is that we begin with some initialization, and then what we do is that we linearize the constraint around that initialization. And once we do so, what we have is an L1 minimization problem subject to a linear constraint. And so that can be solved by solving a linear program. And so that's what we do. We solve that linear program. That linear program is not enforcing the unit norm constraint. And so the solution to that linear program needs to lie in that red line, and it's outside the sphere. So what we do next is to project that onto the sphere. And then we linearize again, we find the second solution, and then we project. So what we're doing, therefore, is just solving a sequence of L1 minimization problems subject to a linear constraint, all of which can be solved by solving a linear problem. So that's what the sequence is. And our hope is that this iterative process will eventually converge. And so if yes, what does it converge? And is it really solving the problem I started with? So that's something we did the analysis of, and we were able to show that if the initialization is sufficiently far from the inlier hyperplane, so very similar to what you do in the power method, that if you cannot start it from the subspace, right, then this sequence of linear programs converges, and it actually converges in a finite number of steps. And the reason is that you can find a lower bound for the improvement at every iteration. So that was the first algorithm. The second way to solve this problem is to apply iterative reweighted least squares. So in this particular case, the idea is that we have to solve this optimization problem. I apologize that I think I'm missing here, so let me annotate. This should be the jth data point here, right? So it's sum of distances subject to an L2 constraint. Then we can put the square in the numerator and just the distance in the denominator. And once we do that, we can now, starting from some initial normal, we can consider, I think here, this as a weight and make this weight fixed. And once we do that, the objective is now quadratic. So this is now the sum of weighted square distances subject to a unit norm constraint. And now this is a eigenvector eigenvalue problem. So the B is an eigenvector corresponding to the smallest eigenvalue of a certain matrix, effectively the data matrix, but weighted by this quantity over here. So that's the second approach. So this can be done, as I said, using a singular value decomposition or an eigenvalue decomposition of the data at every iteration. So this method is more efficient than the linear program. We've been able to scale it up to on the order of 6,000 data points. It works well in practice. It seems to converge, but we've not developed the theory of convergence yet, though we believe it should follow from some of the results from Dobitsch's about iterative reweighted least squares for L1 minimization. The challenge here being that it's a non-convex problem, so there is an extension that needs to be done. Okay. The last method, perhaps the simplest, in fact, this is a quite trivial method, is simply apply the subgradient. So the subgradient of the objective is given here. It's just the sign of the X transpose B and multiplied by the data. And this is what we do. We compute the subgradient. So again, as before, we start with some initialization. We compute the subgradient and we move in that direction. When we do that, we are outside the sphere. So then we project back onto the sphere. We apply the subgradient again. And then we project. Okay, so the two challenges here is that now we have a step size and also the analysis of convergence and whether it actually converges or not to the global minimum that we care about. So what we have proven is that we have proven that it does converge, and we need to have a suitable initialization. So in this particular case is the spectral initialization. So this is just writing down the equations of the projected subgradient method that I just described. So you just follow the subgradient with a step size mu k and then project onto the unit sphere. And the only clever ingredient here, because obviously this method is well known and trivial, is the selection of the step size. So rather than selecting it as a constant or just diminishing exponentially, what we do, and this is illustrated here with the green curve, is that we keep it constant for a number of iterations. And then we decrease it by multiplying it by a number beta that is less than 1. And then we keep it constant for a number of iterations, capital K, and then we multiply by beta again. So the step size is piecewise constant and is piecewise diminishing in the sense that is diminishing by multiplying it by beta at every iteration. Okay, So piecewise geometrically diminishing, and that's what the formula at the top says. So the main theorem really is that if the initialization is smaller than a fixed angle, and this angle was the same as in the very first lemma that I presented today, the one that ensures that there is no critical points, and that theta sharp is actually very close to pi over 2, if you remember from the analysis I presented at the beginning. So what this is saying is that actually from most initializations, okay? And so if the initial angle is small, but not that small, just roughly speaking less than pi over 2, then if you follow this algorithm, the tangent of the angle theta k between the kth iteration of projected subgradient descent and the true normal to the subspace is less than or equal to something like beta to the k. So that's what you see here in the blue curve. So that's going to be exactly the tangent of theta k as the iterations proceed. So, and what you see on the top right is an upper bound that we have derived in our theorem. And so again, what this shows is that the algorithm has a piecewise linear convergence rate, and it's exactly determined by beta, which is the rate at which you decrease the step size. So in summary, I've presented 3 algorithms. The alternating linear programs, that is converges in a finite number of steps, but it actually is not very scalable because it requires solving a linear program at every iteration. The iterative reweighted least squares, that we don't have a theory proving that it converges, but it's more scalable. We've tried it here with 10 to the 4 data points. And the projected subgradient method, that is both, we have a theory for convergence, but we also are able to scale it to say 100,000 data points. This is just a numerical experiment on synthetic data, where you see here the ambient dimension is 30, the subspace dimension is 29, so trying to estimate a hyperplane. The number of points is 500. And then there is an outlier ratio of 0.7. Okay, so 70% of the points are outliers. What you see on the left plot is theta as a function of the number of iterations. And what you see on the right is theta as a function of time. And theta should converge to 0 because it's the angle between the estimated normal and the true normal. And what you can see is that maybe let me just concentrate on the time, which is at the end what we care about, is that the projected subgradient method, which is the blue method, is one of the fastest. But in fact, we have 2 implementations of it. One with this piecewise geometrically diminishing step size, but the other one is using a modified backtracking line search. And that is actually the best method. That's the red curve, or not the best, but the fastest. And we don't have the theory of convergence for that red one. So the one for which we have the theory is the blue one that I presented today. And the other methods are clearly slower. So the projected subgradient method with a constant learning rate eventually just gets stuck. And the iterative reweighted least squares is slower, and the alternating linear program is also slower. Both of them do converge to the global minimum. Okay, let me. I'm going to skip this, but the main point is we have extended this to noisy data as well, and we have all of the theorems about global minimum. So very similar flavor. And also the fact that we can tolerate up to a square number of outliers, even with noise. And also the same theorem about piecewise diminishing with step size. The convergence of the projected subgradient is the same method, same optimization problem, is also applicable in the noisy case. And the primary difference is that the rate here is the same, but then there is an extra term that depends on noise, meaning that you're not guaranteed to convert to the true normal to the subspace, but rather you're close to the true normal. And how close? Roughly square root of sigma, which is the amount of noise as shown here. So let me briefly show you experiments. These are the same that I showed you before, so I'm not going to repeat them. Let me go to real data. So this is data that is collected with a car, and it's point cloud data. Essentially, you have a car that drives through the streets in Europe. And this is a data set that was published in 2013. And in this particular case, the inliers are going to be all of the blue points that correspond to the ground plane. All of the points that are not on the ground are going to be considered as outliers. Typically, each frame of these videos has on the order of 100,000 data points. And typically here, the number of outliers changes, but it can be well around the average number for the entire data set is 53%, but it can be more or it can be less depending on every individual frame. And this is an example of different frames of the video, and this is annotated, as you can see, with all of the blue points are those that correspond to the ground plane. Okay. So what we do is that we run a variety of different algorithms, ransack, projected subgradient method, Reaper, and whatnot. And then once the algorithm finishes, you're able to estimate the ground plane. But then you can also assign points to the plane or not. So are they inliers or are they outliers? And you typically declare them to be an inlier if the distance to the plane is less than some threshold. And now you can vary that threshold and produce what is known as an ROC curve, right? So as you vary the threshold, you have the false positives, the false negatives, and you can compute these F1 measures, right? And so if you do a good job, meaning that most of the points that you declare to be on the ground are on the ground, and most of the points that you declare to be outside the ground are outside the ground, then across all possible thresholds, that's what this F1 measure is trying to compute. And so it's the area under the curve, and the larger, the better. So if you had an area of 1, then you will be doing a perfect job. So the numbers here therefore show that the DPCP method that we have developed based on projected subgradient gets 0.93, while other methods that I mentioned, the Reaper, the low rank plus sparse style decomposition is actually 0.2, so it's much worse. And these random sampling methods, it's way worse. Now, it can be pretty good, but it's a question of time. So the projected subgradient method usually takes on the order of 100 milliseconds to do this, and ransack is based on sampling. So what we did here is to say, okay, let's give ransack the same amount of time, and it got 0.023. Let's give it 10 times the amount of time, and then it gets 0.62. Let's give it 100 times, and then ransack, because the more you sample, right, eventually ransack is going to find the right solution. But the problem is that it takes a lot more time. Okay. This is just testing on many other frames and telling you what is the area under the ROC curve, and showing that for some frames we get 99%, 99%. Here, for one frame, ransack did better, but it requires 100 times more time to do it. So by and large, I think this is demonstrating that across the board, this method is sufficient, scalable, and it produces much more accurate results, both in synthetic experiments as well as in real world data. So in summary, what I've done is to show that a fairly straightforward and simple problem formulation of minimizing some of the distances to a hyperplane subject to a unit norm constraint is one of the first methods that is able to recover subspaces of high relative dimensions like hyperplanes with pretty much perfect accuracy, with tolerating outliers up to about 60%. And it can tolerate more outliers, but then the dimension needs to be a little bit smaller. And it only fails in the very high dimensional regime with a very high number of outliers. I've also presented algorithms for solving these problems that are efficient and scalable, and that are provably convergent to the global minimum of this problem. And by and large, the method works when the data is well spread out, and the outliers are also well distributed. And the other thing that it can do is that it can tolerate a very large number of outliers on the order of the square of the number of inliers. With that, let me just thank my collaborators. So the original developer of this method is my former student Manolis Tsakiris, who is now an assistant professor in Shanghai Tech. He did the DPCP 1.0. And then Zhihui Zhu was a postdoc who developed the second version together with my student Tianjiao Ding, actually, and Daniel Robinson is actually the main supervisor of Tianjiao, and I co-supervised. Thank you very much, and happy to take questions.
Thank you, Rene. Thank you so much for a great and exciting talk.